Hello, welcome to the panel session, and we've had two great talks which have really set things up. So before we get on with discussing, I really should introduce our three experts here. So I'll start with the order they are on my screen. So we've got Paul Master at the top there. He's from Cornami, and he's got wealth of 30 years experience of design and stuff. He's been in startups, he's been in big companies like Boeing, etc. And yeah, so he's got a wealth of experience that he can bring to the table. It's great. Next one on my list and on my screen is Ingrid. She is a professor at KU Leuven and one of the co-founders of Belfort, who you've just heard from. And she's got tons of papers to her name and ERC grants and whatever, so also well known. And we have Rosario Cammarota from the US. He is well known in the US community for his work pushing FHE hardware in Intel. He's chief scientist at Intel Labs, and he's been very active in DARPA's DPRIDE program, international FHE standards, and he's got lots of stuff to his name. So there you go. We've got three amazing people representing one big company, one kind of company that's been there for a while and it's growing, and one tiny little minnow that's just started and wants to grow into a whale. So we've got loads of, we've got a great difference there. So we're going to start with a few questions, and what I thought we'd kick off with is just give me your feeling about what performance improvements have we seen with FHE in hardware up to now. And what can we expect to see as things change over the coming years? So, you know, look forward a bit and also look back a bit, and try and put the audience in the place of where we really are now. Who wants to take that first? Ingrid.
I guess I have to unmute myself for that. So thanks for the question, putting me on the spot. I do think we have seen, if you say how much improvement, then it's often where do you start from?
Exactly, yeah.
And so I have seen announcements of 100,000, whatever, but if you compare to one CPU, yes, you can get those numbers. And that's what he was saying too. We compare at least to one of these really high-end 64, 192, whatever, 196 CPU cores reference. And then we try to compare and see which you can improve. And I think on FPGA, compared to those, you can get factor of 10, I would say, but I'm compared to 192 type of machine. And I think for ASICs, you can at least get another factor of 10 there. And then it depends what technology you're using. Don't forget that if I'm using FPGAs, I also have access to high-end technology, right? This is 7 nanometer TSMC. Paul can maybe add to that, but if you want to make a chip in 7 nanometer or 3 nanometers TSMC, you're gonna need a lot of money. The second thing, what I think we see a lot of improvement is that actually on the algorithm side, lots have improved. And that's just the people, the mathematicians like you, who come up with cool tricks to get things running faster, or reduce the number of bootstraps you need, or reduce the number of, the representation. There we can save a lot. And then the third factor where I see a lot of progress is, for instance, the example of the Leuvenstein, is that you make your application FHE friendly. If we go straight forward, take the way we learned how to, I don't know, what kind of algorithm, sorting in school, in computer architecture class. There's no way you're gonna sort like that in the FHE or database lookup or whatever, right? So you have to switch and you have to make it FHE friendly. And that's the way actually in the old days we were used to make hardware. In hardware, we also work with multiplexers and don't sort the way the software people sort. So I think there's 3 levels you make improvements.
Cool, thank you. Paul, do you want to add anything to that?
I do. So let's take a look at the future. So we're not anywhere near milking algorithmic improvements, right? So the algorithm is the king of the battle, right? A better algorithm means will speed up anything you're running on. Better algorithm, better software, better hardware, try to combine them together, and you can do some magic. So one of the world's worst kept secrets in fully homomorphic encryption is basically encrypted large language models, right? So you look at that, and initially you look at a large language model, massive amounts of compute, right? It's a sledgehammer of matrix multiplications. And then you want to toss FHE on top of that, and you look at that, and you wind up with an exponential explosion. Okay, so this is where the algorithm comes into its own. And we just published at the AI conference in Santa Clara last week some of the algorithmic improvements that Craig Gentry has been doing. That man is like a hurricane of algorithms, which is awesome. So we take a look at the building block of a large language model, which is basically a matrix multiplication. And if you compare it to, I got to do a ciphertext multiplication by the number of parameter blocks, blah, 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 you're never going to get there. But that's the starting point. And then you start optimizing the algorithms and you say, wait a second, I don't need cipher mult. I can get away with plain text cipher mult. The cost comes down. Then you take a look at it and said, why am I doing a mult? I'm not doing a mult, I'm doing a matrix multiplication. And the algorithm gets better. So current state of the art from a cipher plain text mult from, pick one of your favorite open source frameworks to where the algorithm is now is almost 200,000 times better. So yeah, we're nowhere near milking these algorithms, and I suspect this will continue until FHE turns into basically like Bitcoin. The algorithm will never change after that point. So early days, exciting days. I think we're going to change people's perception of where FHE can be applied.
Cool. Ro, do you want to add anything?
Yes, can you hear me?
Yeah.
Excellent. So two things. So the first thing I do want to say a couple of words about algorithmic improvements. Okay, definitely the better algorithms is better than anything else to improve performance, and you should use it. But it's also true that the better algorithms kind of level sets. You will improve performance pretty much on any architecture. Okay, so now let's assume that we have the better algorithms. So the state of the art of FHE today is FHE on GPU. Let's forget about CPU. Okay, and compared to that, to your very initial questions, in the latest technology node and within the area constraints of what we had, we designed basically, we have stations and platforms working in our labs, and we have this chip that was designed to have a very stringent area constraint. In the latest technology node, you can get 100x better than GPUs today. But I also want to add a note of caution about these speed ups, right? Because speed up per se doesn't necessarily relate to an application, right? Today, there are plenty of applications that we historically in the community have tried to avoid the bootstrapping like the worst thing that you can do ever because it's very costly. That actually on hardware acceleration, they run a lot faster than unencrypted computation, but like a lot faster by a large margin. So I would say that while we will keep chasing FHE with newer improved architecture, like for example, a new technology nodes gives you the opportunity to improve your architecture by keeping the same area. If you are okay with that cost of silicon, you can do a lot better, okay? Improving algorithms, that gives you another number of X's, hopefully, but algorithms don't come around every day, new algorithms and things. But I would say today, with do have the tools and means basically to deploy FHE for the majority of applications. FHE have already been envisioned and somewhat proven, but not deployed because there's still a gap of performance. With the advancement that we have achieved in the past 4 years, it's been quite a remarkable time window, to be honest.
Cool. Okay, so there's there are various techniques you can use. Okay, we saw one of the slides said you've got CPUs on one side, which are super general and can be used for anything. And then we can go through, we could have like, I don't know, you could have GPUs, we can think of FPGAs, we can think of custom hardware, custom chips, or we can think of general purpose chips, but which are specifically designed like ones which are like multi-tiled processors with various different interconnects, which are kind of a bit more general purpose than specific things that, for example, like Optalysis we're talking about. What are the different trade-offs when it comes to FHE acceleration? And specifically in relation to, we want to accelerate FHE, but we might not actually know in our application which FHE algorithm we want to accelerate, whether that's CKKS, whether that's BFB, whether it's TFHE. They've all got different characteristics. And all those different implementation techniques, CPU, GPU, tiled processors, FPGAs, dedicated hardware, or all have very, very different metrics. How do, you know, that's like a three-dimensional chess piece puzzle we have to solve. How do we address that? Is there anything that is commonality? Do we think there's going to be one bullet that solves everything, or whatever? Ro, do you want to start on that one?
Yes, I would love to start on that one, and I would actually also kind of follow up on something that Flavio was talking about in the very first presentation, right? I talked about the Optalysis stack, at least to some extent, in its middle, to be you know, rooted on the Intel polynomial instruction set architecture stack to begin with. You know, fundamentally, you know, we made the choice there. And we made the choice that, you know, homomorphic encryption, modern homomorphic encryption, it's partially true, okay? But let me get away for it for a second, and then I'll tell you why I think it's all good in the end. So modern homomorphic encryption is homomorphic encryption on polynomial ring. So our assumption basically was, you know what, we needed to elevate polynomial ring arithmetic as a new data type. It's not a fundamental data type, and use basically this abstraction to do two things: to have a tool that can be used to design an instruction set architecture, and then the architecture, and then adopt the best circuits under it, and to have also a tool basically to be able to front-face cryptographers and experts in the field that want to implement new schemes, okay? And on top of that, then you can embrace very easily applications, right? Because it becomes very similar to a library, but it gives you a lot of flexibility. Now, you know, if we move from ring LWE specific FHE schemes to kind of the more modern version, and more modern versions, I'm talking about schemes based on GFSW and other combinations basically of algebraic structures together. Clearly, when you look at their implementation on CPU, right, they rely not only on polynomial arithmetics. There are scalars, there are all kinds of other things. And even if it's not fully necessary, the first implementations of the schemes that were more practical were even using FFT, like real numbers. Okay, so now we kind of to abstract what is the mathematics and what is the commodity basically of implementing these schemes on existing architecture, because now we have new architectures, and we have new architecture because of the need basically of bridge the performance gap. And what happened, this is a conversation that I actually remember having with Ingrid probably a year and a half ago, and we resonated to that. By the way, I'm honored to be on the same panel with you, Ingrid, okay? This is like a good right? Where we were talking about a new architecture are posing the new questions that needs to be solved at the algorithmic level. So actually now you have an algorithmic co-design, not so much of a hardware-software co-design, and that brings innovation on the algorithms side. So one thing that I thought a lot with my team, that they wanted to take an implementation and then hammer it on the hardware or co-design that software implementation. It's like, wait a second, why don't we look at it from a different perspective? Right, and can we actually change the algorithms in a way that you maintain the key characteristics and features of the original schemes and security in particular? Let's not forget about security. Otherwise, I know how to run things faster without security. Okay, we know that already. And so, from my perspective, to your point, the ring polynomial arithmetic is still a very useful abstraction because it allows you to handle the scale of these problems. Today, it's not that we don't know how to do vector architecture. Intel has done this for a very long time. And it's not that we don't know how to use polynomial arithmetic. In communication engineering, you use that all the time to transfer data and code. And it's modular polynomial arithmetic, okay? It's like the similar kind of things, at least there are nuances. The point is the scale. The polynomials that you use in communications have 30 coefficients, the degrees 32, 64, and things. Now we have 100,000 per polynomials, and it's a tensor of polynomial per ciphertext. Okay, and then you need the simultaneous interaction of these things. From a hardware perspective, it's a nightmare because the scale of the problem is really, really, really big, and achieving performance in very small space, it requires very specialized skills. Okay. So to me, the polynomial ring arithmetic is the unifying glue to all of this. And then you have flexibility up and down the stack on how you design and do things. And it's very similar to what Flavio was explaining to us in the presentation, where they want to map that on an optical architecture.
Paul, how would you address the
let me dive into the details.
Algorithms and the different hardware possibilities.
Yeah, we're still in the area where the math primitives or the key math primitives are somewhat schema dependent, right? So are we doing double precision, small order FFTs? Or are we doing very large polynomial NTTs? The math engines underneath vary very differently. So at this point, we still need, so you have two choices. You can use a generic engine and you will have to call it many, many times to implement the latest flavor of the math primitive. Or you add enough flexibility to be able to change that kind of sort of like an FPGA to try to super specialize it. Those are the two design decisions at the very bottom. But if we take it up a level, I think what we can say is basically the size of the data that we're moving now is so large that conventional memory architectures become the bottleneck, right? So you cannot, touch a memory, right? So if you're touching an external memory, it costs me 1,000 times the power, not to mention it's slower than all get out. If I touch an HBM, it's going to cost me 100 times the energy. Not to mention it's 1,000 times the cost, or not 1,000, but 100 times the cost. So we have to build machines that are going to be efficient at these high order, high dimensional vectors. And, FHE I put in that category, large language models I put in that category, new algorithms that are being developed in different categories. The world is going in that direction. So we're going to be moving massive amounts of data that cannot be going in and out of memory all the time. So from an architectural point of view, this is exciting because this is where new architectures come from, because there is now a demand for us to be clever and not just you reuse the same old stuff because it's good enough. The same old stuff is not good enough anymore. So it's the heyday of architectures.
It reminds me of something from my days at HP when the phrase was try to remove the compute to the data, not the data to the compute. It's a very, very similar idea. Ingrid, do you want to patch in on that on this conversation on this point?
He has a good point. Huh? You move the compute to the data, and there are cool new things to do. It's called in-memory compute, or things like that, right? But in-memory compute is only, and in-memory compute could be applied to these things, but we have to figure out that we're not starting to move the data around. So one of those things. Also, I think supporting multiple schemes. One thing I notice, but I'm not a mathematician, is that some of these schemes are actually moving a bit towards each other. In the sense that, for instance, FHE is working not just on booleans, but because short ints and using all kinds of tricks to not just have 4 bits, but maybe also go 5 bits. And I saw last crypto, I think, people that move the CKKS down to only 12 bits. That's not a big difference anymore.
Yeah.
Not sure how the math works. I'll have to come and ask you. So there we can get inspiration. And then how this architecture is going to look like, that's really cool. That's the 1 million question. So yeah, these are the kind of tricks, right?
Cool.
Yeah.
Yeah.
Go ahead.
So there's all 3 of you working for companies and hardware companies, and there are a bunch of people on the call who probably aren't working for hardware companies. They're probably working for people trying to make FHE applications. There might be some academics wanting to see whether they can make their stuff useful in the real world or whatever. But one of the problems with hardware is that it costs, especially when you want to do custom stuff. And if you want to build your own stuff, it costs millions just to make your test chip, let alone, and therefore for investors to get their money back, you have to produce at volume. You don't get your tiny nanometer factory to produce chips unless it produces quite a lot of them. So where do you think are the FHE application areas where we are going to get the volume of application to justify the fabrication of large amounts, or at low nanometer technology, large amounts of chips? Paul, do you want to address that one?
Yeah, so just to toss it out to, building submicron geometries is hellaciously expensive.
Yes.
So I'll just pick a number, right? It cost me $100 million to build a chip at some technology node.
Yeah.
I need to sell a lot of chips to, justify that $100 million investment. Okay. So what we need is volume. I have white hair on the top of my head, so I'm going to use 1990s technology, right? We need the killer applications that have enough volume to justify the investment and the continuing investment in these chips. And so right now, and this is a moving target because this entire community is discovering we're doing new stuff, we're going after new areas. So from my point of view, there's 2 areas where I think we have hits. So one of them, kudos to Zama basically, but the encrypted smart contracts. I think that is a volume area that will, we can feed silicon to that for a long, long time. The other area, as I alluded to, basically is these encrypted large language models or small language models. But anyway, what we're calling private LLMs, and that term got hijacked a couple of weeks ago anyway. But I'll tell you that because we're out talking to real people that use this stuff. And when I went out there, you talk to these guys and you think, well, most of them couldn't care less about security whatsoever, right? I don't care about your security. I don't care about your personal information. I don't care if my stuff gets stolen, couldn't care less. What we're finding is there is an inherent demand for this, either due to, regulatory issues, kudos to the EU for GDPR, customer requirements, government requirements. And so, just to say, it kind of warms my heart, but, I keep an unofficial poll and about, 2/3 of the people couldn't care less, but 1/3 do. So I think those 2 areas potentially have enough volume to actually keep a couple startups, fabless semiconductor companies busy. So
Cool.
really hopeful. You know, the early stuff is looking really good. So we will find out here very shortly.
Ingrid, do you want to chip in?
Yes, I want to chip in. I did this hand exercise, and one thing also is if you want to get your LLMs running, even unencrypted, these days you need these huge compute farms, and for every compute farm they need to add a nuclear power plant next to it, because these GPUs are horrendously power hungry. I took some numbers for my chess presentation last week from The Economist. So if they add all the GPUs sold by NVIDIA this year, all these new Blackwells and whatever, the amount, and of course, if you buy a GPU, you also have to run it. You're not going to put it as a decoration on your shelf. That would require doubling of the power infrastructure in the US alone. There is currently installed something like 23 or 25 gigawatts. They need another 25 gigawatts to be running by only the GPUs they've sold today. So there is a huge power issue. And I think and even if we only get a factor 10 or a factor 15 or a factor 100 out of ASICs, if we can reduce the power with a factor 100, we also have solved some problems.
Yeah.
Raoul, do you want to chip in on that one? I like my chip in.
Yes.
Yeah, I can.
Yes, I do, actually. I totally resonate with Ingrid's and Paul's comments, right? So in my opinion, we are at that point where there is sufficient so we have talked about this problem for 7 years, that the big corporate have justified interest, to protect their data. And now the regulations basically, started being enacted very seriously, so that there is no justified interest. There is interest in protecting the data. That's the first thing. There is also that with the hardware and standards, the importance of standards is that you get things like FHE outside of the community of experts, which actually count probably less than 50 people all over the world. Right, compared to 8 billion people, 50 people is not an elite; it's a minority, really, so to speak. And so, there is more confidence in the technology. There is the hardware, these platforms that help to prove the technology, and there is the interest that is more than justified today. So, based on, so this is one part of my answer. So there is appetite for ingesting platforms, for example, into data centers, okay, that do FHE. And now the question, towards what Todd was asking in the chat and Ingrid talked about is like, well, we can do FHE on GPUs, and it's not necessarily the most cost-effective things. In the very beginning, you asked the question about, what performance are we looking about, and I told you, 100x better performance than the state-of-the-art GPUs on things like CKKS, perhaps PGB, for people that know how to do it on 32-bit, and things. But actually, when we talk about the things like Interrelacless, those performance is achieved basically on a quarter of the area of a modern GPU, and for half of the power consumption. Okay, so that gives you an angle that if a data center that will ingest, and this is not to say GPUs are great devices, okay? If you pay $1.3 million for each megawatt per year, right, you have a lot of settings and you achieve privacy. Now, where is the play for FHE hardware? Is it going to replace GPUs? Is it going to replace? So now that's not going to happen, okay? But there are two angles that we need to look at, in my opinion. So the first angle is basically that the architecture for serving all this automated intelligence, right? It's going to be heterogeneous. Nowadays, even academic papers, are disseminating this knowledge. And so you would think that, your typical rack is going to have a CPU, high-end GPUs, middle-end GPUs, ASICs. So these FHE ASICs are one of those ASICs, okay? And they not only can do, unencrypted computation encoded in polynomial arithmetic without encryption, and they do it pretty efficiently, but they can also be used basically opportunistically, right? Because until now, we're talking about performance, power consumption, cost, which is all that matters at the end of the day, okay? But we also need to think about security. So you will have basically a host of systems, or even a host of system on the same die, right? Where part of these are going to be trusted, part of these are going to be untrusted, but you won't exploit all of them. And FHE may become a vehicle to opportunistically exploit the untrusted hardware. Okay, so to me, there are various aspects. The latter one is one that makes me more excited because I'm wearing my research hat, right, as a system person, and I'm like, wow, this is great. Where is this going? But the previous part is actually more concrete. So there is demand within data center, and it's shaping because of where the demand for AI inference workload is going. Okay, and the concern with respect to protecting data from the point of view of enterprises and data centers.
So kind of what I've heard is actually, when my first question was actually stupid, in the sense that I shouldn't really be looking at how fast does hardware make me go. What I should be really looking at is what my total cost of compute is, for a given performance metric, which is good enough for the application. How many dollars am I spending on the hardware? How many dollars am I spending on coolant? How many dollars am I spending on the data center? How many dollars am I spending on electricity? And that's really the metric. So all these academics chasing, I've got something faster than you, are really looking at the wrong thing. They should be looking at how am I cheaper than you should be the thing we're talking about. The overall cost is what I've heard from those answers. Would that be a good summary?
And yes, it is, Nigel. And if I add one more sentence, do you know why you are hearing about the cost today and not before? It's because it's becoming concrete. Yeah. This is becoming a concrete thing. And before, we needed to make the proof of concept, right? And that's where all the academic, now it's becoming concrete. So,
okay, great, cool. So we got, like Paul said, there's space for 2 startups. I hope there's space for more than 2 startups because we've got lots of startups in this thing today. So I hope there's more space for more than 2 startups. But that means there's going to be lots of vendors, and we can have lots of different platforms because we've got lots of different applications. We've got the encrypted LLMs, we've got the blockchain, we've got medical data, we've got blah, 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 lots of things. We've got lots of sort of middleware applications like the Google Hair compiler, compiling things around. How important is interoperability to enable widespread adoption here? I really want to focus on, I want adoption. How much emphasis should be put on interoperability versus how much emphasis should be put on actually just making things go faster and meet the performance metrics we need? Let's go back to Ingrid to start this one.
Okay, you're asking always me the tough questions.
You're the professor.
Yeah, sure.
We're okay with that.
I don't have business hat yet. I do think that like in some other fields, what will probably happen is that there is room for more than one solution, depending on where you want to go. I think if you really want to go for, I don't know, high precision or low latency, you might have one stream of application or parameter sets. For instance, if you want to have something that works in bulk or can do your fancy LLM, whatever, I mean, you might, this is going to differentiate a bit, right? I think there's going to be room for multiple. What I do think will be important for that is a set of benchmarks. And I hope that later Shruti talks in her talk about reasonable benchmarks. Nobody cares how fast your NTT runs, right? Because who cares how fast your NTT runs if you cannot feed it with all the data that Paul was mentioning or Ro was mentioning. So an end-to-end application, start with something simple, a simple MNIST. How many FHE versions of MNIST have we seen in reasonable numbers? A simple transciphering. I mean, that's our applications I think we should be in benchmarking. And maybe one scheme is better for one class of applications than others. But it's not out there which ones will go, right?
Todd, what do you think about interoperability? Sorry, I was looking at...
I think...
what do you think about the interoperabilities?
Yeah, so I mean, there are two different angles to look at it. So first of all, you know, there's the standardization part. And many, you know, have been coming after me and say, oh, but you are not defining the specific interfaces and things. And I'm like, we're very far from it. You know, FHE by itself is a very ill-posed technology, okay? Because the cryptographer thinks that it's a security technology, maybe. Application people, is it the thing? It's not very clear to how to integrate FHE into data pipelines. I actually, one time I presented to the CTO of Microsoft. Okay, so Mark came into the room, looked at me, and it was like this, Rob, let me start with this. I'm very skeptical about this technology. This was like 3 years ago, okay? It's not that it's not skeptical today, I believe, I don't know. But, you know, he told me 3 things. So the first thing was, hey, performance overhead is unbearable. It's very difficult to program FHE applications. And see, this is a CTO talk, 3 very crisp points. And it's very difficult, basically, to integrate FHE into existing data pipeline, which I think is the real problem. So at the end of the presentation, what he looked at me, you convinced, the performance is solved. You convinced me, okay? And then, but the other 2 problems, like doing a good FHE application automatically is still partially an open problem, even though we have made a lot of progress. You know, HAIR is one of those. In 2020, we had Graph HE, then Microsoft Research had the chat, you know, to translate the AI application into FHE, and they were doing a pretty good job by the way, okay? But the integration into data pipeline, we are still not looking at it. So to me, when we're talking about interoperability, there are 2 aspects to it. So the first aspect is that, can I get a Belfort solution and an Intel solution and put them into an ecosystem and they talk to each other? That would be very much desirable, okay? But that comes when, you know, the ecosystem grows to a point that it gets, okay, now we can start sharing revenue. So we are still where revenue is not there yet, okay? It's very early. But the problem of addressing the interoperability on how FHE fits into a real data pipeline, that's actually a key problem to solve. Because otherwise, you know, all this technology, with all the boost to the confidence from a community beyond the FHE community and things, is not going to grow into something that will find adoption.
Oh.
Yeah, I agree with both what Professor Ingrid and Rose said, and I, pardon me, and I think this is a case where we have to start growing this, because we are in the early phases. Ultimately, you want the interoperability, right? So we want an end customer to have an application, and he wants to be able to run it on all available hardware that's out there. Whether he does it in a conventional approach or 1 or 2 or 3 or 4 different accelerator approach, at the end of the day, he just wants the ability to run the application independently of the hardware it's sitting on. And we're far away from that. But, you know, this isn't something that's going to get born initially all in one shot. We are going to have to evolve this, seesaw it into existence. So yeah, we got a lot of work ahead of us. And yeah, don't get me started on micro benchmarks, utterly useless. And we're in the middle of benchmarking wars 101 in the LLM space. We need to get to a spec mark, a collection of applications, and that serves everybody.
Like
So
impact.
until, yeah,
Like
yeah, exactly.
Like an impact. Yeah. Oh,
Yeah.
For those youngsters in the audience, impact was linear algebra, a sequence of algorithms that we very important in the 80s. And yes, sorry, showing our age. Right. So, what do you think is? We kind of everyone's got a roadmap, yeah. So we got these. So but in some sense, what's going to be really important is the things that are not on the roadmap, the things we don't expect to happen, that are going to make things go much better than we expect them to do. What are the breakthroughs that we're not, we think might happen, but we're not going to put them on the roadmap because we don't want to promise them to our investors, if you see what I mean. So where do you think the breakthroughs are going to happen in FHE acceleration in the next 3 to 5 years? Is it hardware? Is it algorithms? Is it hardware software co-design? Or is it actually finding niche applications which work really, really well? Paul?
A combination of all those. So you need the applications to drive a new industry, right? And we're getting there. We've learned you have to do the co-design, right? You've got to be able to get the application, and maybe the first applications are hand-built. They are. We've got to get to the point where we can compile FHE applications, a non-trivial operation with all these magic parameters you got to deal with that no programmer on the planet wants to worry about. And we then need the ability to get it. So there's niche applications where you don't care about performance, but ultimately in the real world, people do care about either the performance or the power dissipation. So we need all 3 legs of this stool basically to get this moving forward. And I think your original question is, you're asking for the black swan event. Okay, so by definition, you can't pick a black swan, but I have some ideas, right? So what
are your black swan ideas?
Algorithmic changes, right? This is still early days. So I think we have a couple, maybe at least one black swan coming down on the algorithmic side, maybe 2. The hardware stuff, we know how to build hardware. We've building chips forever. We know where the geometries are going, but we need to know what, right? Which means, what are the algorithms? So everything, again, the queen of science, I think, is information sciences. Again, 790s term, right? Algorithms drive all, but business gravity, money drives the algorithms. So I think we're getting to the point where we're coming up with a virtuous circle that will, drive a new industry.
I agree with that. Ro, what do you want to add on? Where do you think what's your black swan going to be?
I think I resonated with something that Ingrid was alluding earlier, that there seemed to be a convergence in the algorithms. I love that, right? Because I think that will create a little bit more of homogeneity in the way you actually look at primarily at the memory architecture for that moment. And many of the tricks in the past 3-4 years, like the fundamental ones, as Paul was alluding, we know how to build hardware. Yes, we do very well, in fact. But the point is, there is still fragmentation in the community. And if I have to make an example here, the standard at ISO IC took probably 1.5 years longer exactly for those type of discussions that were brought up by the community, not by the people in ISO IC that were outside the community. Okay. So there is still that needs to be solved. Once that is done, and I think there is a very nice amount of convergence, as Ingrid was talking about, Integer CKKS. Now the research, moved from Seoul National University to Stanford. Wow, Integer CKKS is a big deal. Then there is, from a deployability perspective, how do we solve the problem of in the CPAD? Well, we envelope CKKS into BFB. That does that. So there are things that, are right there that will make the current architecture just shine, right? We just need to bring those things into the standard. And that, once the things exist, it's only just a matter of time. Okay? So I can see that coming. I can plan for it. And I know exactly how much it takes to do that, right? So the other part of it, from the hardware perspective, the application, you need the black swan. I don't have any black swan, except what we keep hearing usually. Now it's domain knowledge, so it's not black swan anymore. But from a hardware perspective, I actually do believe that photonics will play a role. And I also do believe that in-memory architecture, by the way, myself and Tana Rosing at UCSD, we have the majority of the literature of processing in memory for FHE. Right, so I do believe that that will play a role quite a lot. But the architecture is going to be something of a continuum. Where you will do something in memory, you will have some computer that is near computer that is independent from memory and things, and then you will build an SoC, hopefully chipletized. That performs as well. There are challenges in the architecture there. So there is a lot research-wise and architecture-wise algorithmics that is going on. Some you can see the end of it, it's coming. Others needs more investment in research. Okay.
Ingrid, what's your black swan?
I keep my black swans for myself. I mean, you can say it in general, right? So we do expect algorithm improvements. We do expect, I do believe in heterogeneous architectures, in the sense that you see it already now in these really high-end designs. Heterogeneous chiplet, whatever, one chip does the CKKS, the other one is doing TFHE, and it might be even, and this is experience we have done in the past, sometimes it's cheaper to have two small pieces of hardware next to each other, each dedicated to one algorithm or one application. This was the case in simple filter design. At some point we did it for symmetry. That might be cheaper than trying to merge everything on one multifunctional whatever unit. Something like that, right? That might also be. We have to do the exercise. I haven't done the exercise.
Cool. Please, the audience, if you want to ask questions, please put them in the chat. I'm going to return to one that Todd's kind of put in the chat, but kind of rephrase it slightly, or maybe interpret it in the way maybe he thought it was going to be interpreted anyway. So we can use hardware acceleration, or essentially at the foundation of all these things, we're just basically doing NTTs and FFTs, yeah. So that's essentially all we're doing. And if we look at kind of modern zero knowledge proof technologies, we're also, once we drop the elliptic curve stuff, because that's not post-quantum, so we don't care about that. But we're using the essentially Reed-Solomon coding to do the zero knowledge proofs, which require us to evaluate polynomials at many points and interpolate polynomials, which is FFTs and MPTs. So you see that there's a way that we can bring those two together, so we can have hardware designs which can address both markets. Therefore, going back to the earlier problem, do we have a large enough market to justify going to silicon at $100 million just for the chip out? Can we actually get synergies between the zero knowledge applications and the FHE applications on the same chip to justify the volumes we need? I can't remember when my rotation where I've got to, but I'll start with Paul this time.
Absolutely, right. The mathematical primitives that we use in FHE are kissing cousins to what's used in zero knowledge proofs. The one additional is the Merkle trees, which is a cool bit of mathematical wizardry that I want to apply everywhere at the moment. But that's relatively straightforward to add. I think the real problem with the zero knowledge proofs is it is a very, very fragmented market. So where's the volume in the zero knowledge proofs? And I think the technology is there, dual use silicon is there. I think that one's basically finding the volume application. And, you know, the silicon we're building, I mean, if we do our jobs correctly, we should be able to do the zero knowledge proof stuff. Or we can tweak the next design to be able to do dual use. So, but I think that market is, what do you bet on? There's like 20, 40 different places. No winner, at least from my point of view, has been discovered yet.
Okay.
So I think it's a business problem. It's not a technology problem.
So you think there are just too many types of zero knowledge proof out there all competing that you don't know which one to target?
Yeah, correct.
Yeah, I think there's a bit fragmented. Yeah, I agree. But yeah, okay. Raul, what do you think about this?
Yeah. So I think you know, cousins are not the same entity. Okay. So when we build the hardware for homomorphic encryption specifically, right, there is a lot of, so we talked about the negatives. Okay, it's difficult because of scale and all of this. However, the fact that rings are very well defined and things allows you to exploit a number of structure that you might not find into other mathematical constructs, and for which actually, if you want to optimize a hardware for one or the other, you can do it. But if you want something that mixes them together, to Ingrid's previous point, you will not find the optimal point and things like that. Now, is that the limitation per se? Actually, I don't know. This is a research problem, because when it comes to FHE, you need to see what is the impact, how does the impact basically percolate up to the applications. And maybe not having this such aggressive hardware for rings that are used in FHE and having something that can be used for both, it's not a big performance impact to an FHE, right? It will be a big performance impact for some applications, the simpler one, where you actually have more arithmetic than ciphertext management, okay? But it might not necessarily be a big the impact in the big picture. So I don't know. Yes, cousins, okay, hardware seems to be similar when you look at the block diagram on the whiteboard, but then you go into the details and you say, but these fields actually, if you want to implement them differently, you need to make different choices. And therefore, your circuit looks completely different. So to some extent, you know, at that point, I think a GPU does very well at doing FHE and zero knowledge proofs. Okay.
Ingrid.
Yes and no. I mean, I still think, like, I agree. First of all, a generic entity is indeed at the basis of each of them, but is that your bottleneck? That's the first question.
Mm-hmm.
And then it's again flexibility versus performance. I think in the old days we had the same, and I think at some point it was really beautifully solved by Intel. They had 4 basic instructions to run AES. Way different and way better than anything before that. It was constant time, solved all the cache problems. What you do use there actually is still the infrastructure, the rest of the CPU, but it was solved with 4 basic instructions. And you cannot use these instructions for anything else. The only thing they do is AES. Did we suffer from it? I don't know. I don't think so. And so we have to see whether that's possible here too. I don't know. I don't have the answer at this moment. That's why we're looking at the different possible hardware architectures, because indeed, like Rose saying, some entities, if they're very specific to FHE, you can optimize them very nicely. They become very compact and so on. Yeah.
I remember Ruby Lee, who's a famous designer of chips. She was at Intel, I think, and then she moved to HP or something. And so she was talking, so she'd helped do MMC and the early multimedia extensions on x86. And she wrote into us about 1998 when I was in HP, and she came to HP Labs and she said, you guys need to think about instructions to accelerate crypto. And we just went, what the hell would we want to do that for? That's a stupid idea.
Yeah.
Then of course the AES instructions came out. Okay, yeah, it was stupid. Yeah, we didn't see that. But anyway, it's just like, yeah. So there we go. That's my little story about how I failed to invent the AES instruction. There we go. So there's actually a really interesting one from Siddharth, which is, we've concentrated all the time on talking about accelerating computations. But if I've actually got a small device, maybe not my mobile phone, but an edge, an edge sensor or something like that, and it's actually sending data up to the cloud to be processed in a homomorphic way, these FHE ciphertexts are bloody huge. How is anyone thinking about how we accelerate on small devices just the encryption, or maybe just the decryption operation? Now, maybe I've got a smart card that has to decrypt the output of my FHE computation. So, and because these ciphertexts are huge. So what are people looking at there? Let's start with Ro this time.
Actually, there is a lot of literature that has been looking at acceleration of encryption and decryption of FHE. I think when you go specifically on the decryption side, you need to take care of something that you don't take care of during the evaluation phase, which is side channels. Okay, just because of the nature of the decryption functions. But other than that, it's a kind of smaller accelerator. Right, that practically does polynomial multiplications, some additions, and it has a sampler, right, for the error distributions. That's basically it on the encryption side. So there is a lot of literature that can be even borrowed by the acceleration of post-quantum cryptography algorithms based on lattices. There is that. So that's why probably we don't look specifically to this problem, because the bulk of it is outsourcing computation, right? But yes, there is a problem there. There is also another problem, which is basically, are you transferring FHE encrypted ciphertext? Those are huge. And this thing of saying, well, there will be, or there will always be more bandwidth, maybe yes, but doesn't mean you have to waste it like that. And so at that point, I think keeping the communication infrastructure and transciphering at the point basically where you actually compute, assuming that you don't need to relay these farther than the end of computation. So transciphering becomes in fundamental applications to integrate FHE into the existing communication infrastructure.
Cool. We're running out of time. Ingrid, do you want to have a quick follow-up?
Yes, I would address that problem by transciphering. So I would encrypt with AES and then do a homomorphic decryption of my AES data in the cloud. And we've done some exercises on how much bandwidth you save by doing this transciphering. And so because you have now a bit of extra calculations, let's say, because you have to do the homomorphic decryption then, but you save a huge amount of bandwidth. We've done some calculations on that. And the nice thing about that is that we do know how to do AES encryption, because these are end nodes. And the end nodes need side channel protection, side channel attacks, fault attacks, all of these things. We are developing the technology to do that in post-quantum, and then you can indeed, as Rose say, you can do some of the side channel protections, but it's expensive. Post-quantum, side channel protected post-quantum implementations are expensive, and the problem is not really solved. Way better solutions for AES. And so then, yes, you save both on bandwidth and you pay a price in the cloud. We assume the cloud has power enough, right? We have all these.
You could also you can cost it, because AWS will tell you the cost of sending data to the cloud plus the cost of the compute, so you know what the total cost is.
Yes. And so we have enough, and we assume there is enough power in the cloud, right?
Yeah.
If they've got their nuclear power station. Cool.
Yes, and it's a matter of decimation, right? So transciphering is a good solution. Ultimately, you'll stick a FHE accelerator, which will be teeny weeny. You won't even see it with the naked eye. But the problem is, if you're decimating, it works. If you're doing one-to-one, we still have a problem. So if I'm going to do the process, I reduce processing on the way up. Transcode it. I do the AES decryption into the FHE space in the cloud. But at that point, if I have to move data and there's no decimation, I still have a problem, right? At that point, I'm moving giant ciphertext around. And that is an interesting problem. And there are problems out there where it's a one-to-one or one-to-n expansion of the data. And that's actually a good research area, I think.
Cool. We've run out of time. I want to thank our three amazing guests. I want everyone to give them a round of applause virtually by clicking the round of applause button at the bottom of your screen. Thank you very much. Yay, well done. We're going to hand it back to Ben, and thank you all again. That was absolutely amazing. Brilliant. Cool.
Thank you.
Thank you, guys.